As engineers, let's be honest that one of the hardest tasks to do is to solve complex electronic circuits. But what if I told you that you don't have to do so for each hard problem? This is because Thevenin's theorem exists. This theorem states that for each linear electric circuit, you can reduce it into an equivalent circuit containing a voltage source named the Thevenin voltage in series with a resistor named the Thevenin resistance. And this equivalent circuit behaves just like the original circuit, but from the perspective of two nodes of your choice. So in that case, instead of going step by step through the complexity of a really hard circuit to get the current value or the voltage value or any value between two nodes, you can actually use Thevenin's method. In this video, I'll show you how to use Thevenin's theorem.
This example that I created, we want to get the Thevenin equivalent circuit between A and B. We start by short-circuiting our independent voltage source and opening the circuit at our independent current source. We will have a circuit consisting of only resistors, and our work will be on getting the equivalent resistance. The value that we will get is equal to the Thevenin resistance, which will be equal to 19.67 ohms in this case, and this is our first step. The second step is getting the Thevenin voltage. We get back our independent sources, and we will apply the node voltage method. We realize that we have two essential nodes, one that is the ground at the bottom and the top one. We should also realize that there is no current flowing through the 7 and 10 ohm resistor because the right hand side of the circuit is an open circuit. So now we apply the node voltage method, knowing that VA is equal to V Thevenin because there is no current through the 7 ohm resistor. And after calculations, we will get that V Thevenin is equal to 24.67 volts. And now we draw the equivalent circuit, which consists of the voltage source and the resistance. There is another way to get our Thevenin resistance. First of all, we turn off our independent power sources, and then we assume between the two nodes A and B a test current with an arbitrary value. But we take 1 amp because it's the easiest to work with. And then we will have a circuit consisting of resistors and this test current. Afterwards, we should know that the Thevenin resistance is equal to the test voltage over the test current values, which is basic Ohm's law. And to get the test voltage, we should do Kirchhoff's voltage law. We will have only one loop, and we will apply Kirchhoff's law to get the test voltage, and then we will apply Ohm's law to get the Thevenin resistance, which will be the same value as before.
Only knowing the theoretical side of Thevenin's theorem is not enough. We need to know its use, benefits, and real-life applications in this world. For example, when engineers are building this battery, they studied the Thevenin equivalent of its internal circuit, which consists of a power source and a resistance, in order to know the power which will be delivered by this battery to different connected loads. And by the way, Thevenin equivalent of this battery is done between its positive terminal and its negative terminal. And this theorem is also useful when approximating the voltage and the current values across a house when connected to an electrical grid, taking, of course, into consideration the resistance of the wires and the potential drop. Some of these informations are from electronicsspecifiers.com and electronicstutorials.com.
I hope you enjoyed this video, and please stay safe around your electronics.